take the graph of G and take its image in H, and that'll be the quotient that we want. So we take gamma G to be the graph of G. Then gamma G will be a closed subscheme of Y times T. H, because H is separated, sorry. And moreover, we have, so in here we have this universal closed subscheme Z. This guy factors through this guy by star, just by taking here y1 and y2 equal. You see that y comma gy is in Z, so that arrow exists with y1 equals y2. Right, and the claim is that this closed subscheme gamma of Z, so this is a closed immersion again, this closed subscheme of Z, it descends along this FBPF cover of H, just by taking the second projection here, and just mapping to H like that. And the claim is that this gamma G descends to a closed subscheme of H. So gamma G descends to a closed subscheme Q, closed subscheme Q of H. And the way to see that is to just do descent theory. So descent theory says that if you take this cover Z to H, you can look at the intersection of Z with itself over H. That gives you two projections, P1. I apologize for the notation. P1 and P2 to Z. And what you want is that P1 upper star of gamma G is P2 upper star of gamma G. And normally there would be a co-cycle condition, but since we're working with closed subschemes or closed immersions, they kind of just go away because there's no movement in a sense. These two have to be equal. If that's true, then we do indeed get a Q down here, which pulls back to gamma G. And this guy is, I hope I'm doing this right. Maybe I'm not, but it doesn't matter. We can interchange them anyway. This is, I don't know. Yeah. So we want these two guys to be equal as subschemes of Z plus H, Z, and that follows from star. Again, a little bit of a hassle with star, and so we get a Q. We get a Q in H, which pulls back to gamma G, closed subscheme Q of H. And a map from gamma G to Q, which pulls back, so Q pulls back to gamma G under this composition. And the fun thing about gamma G, of course, is that it's isomorphic to Y, by this mapping little y to Y comma GY. And this guy right here is going to be our quotient. And you can verify that, like, you can check that somehow you can check that y cross y over h is r, and so now you have this FPPF map from y to q, and it's FPPF because this guy is, just by definition of the Hilbert scheme, this guy's a pullback of that, so this is going to be FPPF. It induces R, the equivalence relation R on Y. And so by the example over there, we see that Q is Y over R. And then you know that Q is a closed subscheme of H. H is strongly projective. Is H strongly projective?
Yeah. You rotated the top of the ball.
I did. Well, in that case, what we get is that Q is strongly projective, which is stronger than whatever. I see. I assume quasi-projective here, so I don't get projective here, but quasi-projective. So Q is a closed subscheme of a quasi-projective thing, and therefore quasi-projective.
You also get that y over r is flat. You said it was FPPF during the last part. You said it was flat during the last part of the proof.
I said that this guy was flat.
Well, FPPF.
Yes, I did. So
Sure.
Oh wait, but it doesn't imply that Q is.
no.
No. Okay.
Okay. Moving on. So now, I'm going to be really sketchy. We're going to map div x over s to Picard x over s by mapping one of these divisors to, the defined ideal dualized. We're going to take the pullback of this along the open subfunctor Picard phi x over s. We're going to call it d of phi. It's not going to be div x over s phi. And for nice choices of, we're going to do even more. We're going to look at this diagram. We're going to take d of phi as well, and then just take the fiber product of Picard x over s phi. You get some fiber product p for r. No, p's fine. Right. Okay, this is the diagram we're working with. We know that this is an open subfunctor. Well, it's true. So open and closed, right? It's this guy is a disjoint union of these guys. So this will be a disjoint union of components of this guy, and by some result in SGA6 on this things for coherent sheaves, it'll be a finite union, in fact, and so it'll be quasi-projective by the quasi-projectivity of this div x phi's objective.
Sorry, that's pick phi, or sorry, is the disjoint union finitely many of these pick phis?
No, no. Take for instance the Picard, the P1. That will be like Z, right?
Right. So then we get it's still open in each pick phi.
Oh yeah, for sure. I mean, they're going to be open and closed for
Oh, okay, sure.
Disjoint union. Yeah. For nice choices of phi, you can make sure that nice choices of phi basically means that you get conditions similar to this Guslow-Mumford regularity stuff. For nice phi, this is an epimorphism. It's FPPF. Moreover, this guy is always, I think, projective. At least it's flat and proper. And so, from the example you now see that Picard x over S will be the quotient of d phi by the equivalence relation given by this pullback. And by the theorem, that means that Picard x over S is quasi-projective and strongly quasi-projective and representable. So what theorem Picard x over S phi is strongly quasi-projective. As I said, very, very sketchy. I apologize. So that at least gives us representability in very nice cases. You can also try to weaken the conditions on x over S, and then you get you also get representability results, but they're going to be not representable by schemes, but by algebraic spaces, stacks. So a little bit of a subsection representability. By spaces or stacks. And of course, if you're working with stacks, everything is always a lot nicer. So that's good. So we make the obvious definition. Given f from x to s in schemes, and congregate schemes, we define a stack. Stack Picard underlying x over s on the FPPF side of S by mapping a scheme and S scheme T to the groupoid of line bundles. So not classes of line bundles, but line bundles on xt, which are flat. Over T.
It's automatic, isn't it?
Flat over T is automatic.
Is X not flat over S?
X is not flat over
Oh,
S.
you don't do that. No.
Not yet.
But then how can a line bundle be flat over T if locally on XT it is OX?
That
well,
might be the
yeah.
empty set.
Well,
Give me a second. I feel like. Oh well, sorry. I guess I just took the stack covariance sheaves and just replace everything with line bundles.
I mean, it works. It's just empty, like kind of more often than you maybe want.
no, but look, a line bundle is locally isomorphic to the scheme on which it lives, right?
Yes.
So being flat over T is it's if and only if O of XT is flat over T.
Yes.
So
Oh, okay. Yeah, I see.
so
Yeah.
It's still the thought.
I mean, well, I'm gonna assume flatness everywhere, and so we might as well.
yeah, and then you can drop it there. Yeah.
And then we can drop it, yeah, okay. Which flat over B can be dropped, nice. Right, so the group of, it's just the group point of line bundles on XT. As I said, with stacks, everything is nicer. Especially if you take into account knowledge about flatness. There's a nice theorem about these, namely, they're pretty much always algebraic. Namely, if x over s is flat, which we assume, but let's put it here as well. If x over s is flat and proper, and we assume that, this condition holds OS to F lower star OX is universally an isomorphism. Universally. Then I'm gonna grab a new piece of chalk. There's a lot, and they're all terrible. Then a bunch of things hold, of course. First of all, Picard underline, which I have to find. Picard underline is an algebraic step. So Picard underline x of s is algebraic. Moreover, it's going to be a GM gerb where the gerb structure is given by a scalar multiplication over the Picard sheaf of x over s. And the 3 of Picard x over s, so just the Picard sheaf, is an algebraic space. It's an algebraic space. Sorry, guys. Yes.
I may be the exception here, but I can only claim to have tried to understand what a stack is. I do not know what a gerb is, and I do not know what an algebraic space is.
Oh, I thought.
And
Okay.
I'm not sure if I'm the only one or if this is.
No, I'm with you. No, this will be over in like 2 days.
Sure. It might be interesting to the experts.
It's
but,
like 1 line more on stacks,
okay.
and then we're gone, and we're done with the stacks.
Great. I have a week to
I
learn.
promise. I just wanted to show off.
Okay.
We're very impressed.
Good. That's on camera now.
It's still running.
The proof is.
Can I just ask one question,
Yes,
which
of course.
is not really related to sex?
Okay.
What is the star doing?
What's the start?
It's
What's
the
start?
groupoid, so only the
Oh
morphisms.
yeah, sorry.
Yeah, but line numbers are hard to multiply.
No, but the morphisms
No.
on isomorphism.
Oh,
It
yeah.
says the morphisms isomorphism.
Ah, it's the more.
So I take the category of line bundles and I throw out everything which is not isomorphic. The proof is by checking Artin's axioms. It's really short.
Do you know somewhere where that's written down?
The stacks product. So
Oh, they actually do it?
what he does is,
Cool.
well, he doesn't do this one. He doesn't do this one. What he does is he checks the Artin's axioms for the stack of coherent sheaves,
Yeah, okay, and then-
and then he shows that this is open stuff. Right. Oh, okay. So what's really cool about this? Just a little bit more. I'll be done after this remark. Almost. So this GM gives a Broward class, whenever that makes sense, on the Picard sheaf, because it's a GM gerb. That's just how that stuff works. So in particular, this shows you how this map from Picard x over s t works to the Broward prime.
Should the thing is go back to be underlined?
Yeah.
Oh, which one? Oh yeah, this one for sure. To Broward prime of t. It's just you take the map from t to here and you pull alpha back. Or alpha is this guy. Moreover, well, I guess it's almost done. There's a corollary of this guy, which is pretty fun. It does not involve stacks. So that's good. It's a result of Ort and Muir, namely that if x over the spectrum of the field is proper, then So here you have flat proper this thing. Huh.
You have the efforts or.
I probably should assume something on the fibers. But, well, geometrically integral fibers, why not? You have proper, you have that it's flat, you have this guy. Then, Picard X over S, the sheaf, it's going to be a scheme. It's a group scheme. And the proof, you take this result, the fact that it's an algebraic space, which holds by these assumptions, and you realize that in the category of algebraic spaces over a field, the group objects are always schemes, which is kind of cool. Put it in quotation marks, because it's not really much of a proof, but group objects in algebraic spaces over K are schemes. And that gives another representability result. Can I keep on going? Sure. Not on this. I'm done with this. I want to talk politics now. It's properties. So some basic properties.
Okay, maybe.
Can I just list them? I'll just list them. Erase this. This is going to be a very short section. So this is about properties, the Picard thing. We take S to be the spectrum of the field, and we assume X over S to be all sorts of nice, projective and whatnot, flat, fine representation.
So flat you can drop, right?
True. Field.
And
Thank
fine
you.
representation is a field.
Yeah, very nice. Yes, finite type. Then the tangent space, H1. No. Then the tangent space is the unit of Picard X over S. Is going to be isomorphic to the first homology of X with values in OX. So, for instance, the consequence is that, like, for a K3 surface where this guy vanishes, this will become like a discrete thing. That's thing one. And thing two is that Picard X over S, we have this inequality, the dimension of Picard X over S less than or equal to the dimension of this guy, so H1 X of X, with equality if and only if Picard X over S is smooth over S. In particular, if you're working in characteristic 0, all group schemes are smooth, all finite type group schemes, I guess. So then you see that Picard, the dimension of Picard is always equal to the dimension of this. I guess it's
Is there any questions?
Yes. So in this last case, you have a group scheme over K, and it is smooth, say, right? So it's locally of finite type, and it has a connected component of identity and a group of components, a group scheme of components.
Yes.
Right. So if K is algebraically closed, you get a lot of you get a constant group, right? I mean the group of connected components is a group. commutative group. Can you say anything about how big it can be? Can it
the
be
group of connected
uncountable?
components.
Hmm?
The group of connected
Yeah.
components. No, it's narrow Severi group.
Yeah. So
Which
how
is-
big?
Oh, not very. I imagine.
It's always
finally generated.
countable. Yeah, finally
Countable.
generated. Okay.
Finally
Good.
It's a group.
Okay. And I had another question. You said when you did the blackboard that you were the part that you were standing in front of, that you took some nice phi, right?
Yes.
But we want to know it for all phi.
Oh, yes. To get it for all phi, you use a result in SGA6. Again, one of these boundedness results to be able to change the phi, I guess.
Translate by the.
No, you can't because you see it is over S. So some fibers might have a much more bigger neuron Severi group than others. So the big zero, I think, is the connected component fiber-wise will be nice, but the other ones are very chaotic because they depend on the neuron Severi group, and that jumps in a strange way. So I don't see how you go from one to the other if you have to move, well, yeah, except if you stay in one fiber.
Is an SGA6?
Yeah.
Okay. I think I'll have to check this separately afterwards, perhaps. All right, any additional questions? In that case, let's thank our speaker again.